This is a train that doesn't touch the tracks. It floats, powered by superconducting magnets, capable of hitting 603 kilometers per hour, faster than any wheeled train has ever managed in commercial service. And to build it, Japan is doing something almost nobody expected, burying nearly 90% of the entire route inside solid mountain rock. This is a Chuo Shinkansen, and it might be the most expensive, most difficult railway ever attempted. Let's get into it. Japan invented commercial high-speed rail back in 1964 with the original Tokyo Shinkansen, connecting Tokyo and Osaka, and kick-starting a global obsession with bullet trains that's still playing out today, as we've covered on this channel before. Now, more than 60 years later, Japan is trying to reinvent the concept entirely, not with a faster wheeled train, but with something that barely resembles conventional rail at all. The Chuo Shinkansen uses a technology called SCMAGLEV, superconducting magnetic levitation. Instead of steel wheels running on steel rails, the train is lifted several centimeters off its guideway using powerful superconducting magnets, then propelled forward by a linear motor system built into the guideway walls themselves. There's no physical contact between the train and the track once it's up to speed, which eliminates the friction that ultimately limits how fast a conventional wheeled train can safely travel. In testing, this technology has already reached 603 kilometers per hour, the current world record for any rail-guided passenger vehicle, a number so far ahead of conventional high-speed rail that it's genuinely a different category of transportation. So why isn't this already running decades after Japan first started developing the underlying technology back in the 1960s? Because building it turns out to be extraordinarily difficult and increasingly expensive. The project is being led by Central Japan Railway Company, known as JR Central, aiming initially to connect Tokyo and Nagoya, with a longer-term extension planned to Osaka. The Tokyo to Nagoya section alone is projected to cut a roughly 90-minute conventional bullet train journey down to around 40 minutes. Extended eventually to Osaka, the full journey could take just over an hour, compared to roughly 2.5 hours on today's fastest conventional Shinkansen. Here's the number that's been climbing steadily as the project has progressed. Total construction costs for just the Tokyo to Nagoya section are now projected at around 11 trillion yen, roughly $75 billion at current exchange rates, a dramatic increase from the original construction budget of about 7 trillion yen set out in earlier planning documents. JR Central has attributed a significant portion of that increase to broad price inflation across construction materials and labor, along with additional costs tied to unexpected engineering challenges. So what's actually driving a cost increase of that scale, and why does building this specific train require so much tunneling? This is where the project's defining, almost extreme engineering decision comes in. Roughly 86 to 90% of the entire Chuo Shinkansen route runs underground, through tunnels bored directly through mountain terrain, including a significant stretch beneath the Japanese Alps. That's an extraordinary ratio for any railway, let alone one stretching hundreds of kilometers. The reason comes down to physics colliding with geography. A maglev train traveling at 500+ kilometers per hour needs an exceptionally straight, exceptionally consistent alignment. Unlike conventional rail, which can tolerate gentle curves and modest gradient changes, a maglev system traveling at these speeds requires an almost razor-straight path to avoid the kind of lateral forces that would make high-speed travel unsafe or uncomfortable for passengers. Japan's mountainous terrain between Tokyo and Osaka simply doesn't offer that kind of straight-line path at the surface. Rivers, valleys, dense urban development, and the mountains themselves all force conventional railways into curves and detours. Going underground solves that problem directly. A tunnel bored through solid rock can follow a far straighter path than a surface route ever could, since it isn't constrained by existing terrain features, rivers, or urban development sitting on top of the ground. It's an expensive solution, but for a maglev system operating at these speeds, it may be the only practical one. The single most difficult section of this underground route is the Southern Alps Tunnel, a bore stretching more than 25 kilometers, reaching depth of nearly 1,400 meters below the surrounding mountain terrain at its deepest point. To put that depth in context, that's deeper underground than many of the world's tallest skyscrapers are tall. Constructing a tunnel like this requires an approach called the New Austrian tunneling method, which involves spraying concrete directly on freshly excavated rock surfaces to form an initial lining, and then using rock bolts and additional reinforcement to stabilize the surrounding rock mass as excavation proceeds. Before the main tunnel is even bored, engineers drill a smaller pilot tunnel alongside the planned route, examining the geological conditions and groundwater conditions in advance. In the Southern Alps section specifically, JR Central has used what it calls ultra-long boring surveys, examining rock conditions up to a kilometer ahead of the tunnel face itself, given just how geologically complex and unpredictable this particular stretch of mountain has proven to be. And unpredictable is putting it mildly. Several tunnel sections have run into exactly the kind of geological surprises that turn a carefully planned construction schedule upside down. Rock formations in multiple sections have proven significantly more fragile than initial geological surveys predicted, requiring extensive additional reinforcement work well beyond what was originally budgeted for. 3 specific tunnel sections have seen their completion timelines pushed back by roughly 5 years each, from original targets around 2026 to revised targets around 2031, as crews have had to slow down and reinforce sections of tunnel running through unexpectedly unstable rock. There's also been significant political and environmental friction along the route, particularly in Shizuoka Prefecture, where the tunnel passes beneath a mountain range that feeds a water system relied on for both drinking water and agriculture downstream. Local officials raised serious concerns for years about how tunnel construction and groundwater management might affect that water supply, effectively stalling boring work on a critical central section of tunnel for roughly 7 years while environmental mitigation plans were negotiated. That standoff was only resolved this year when the Shizuoka governor finally approved the start of boring on the remaining central section, a deal that's expected to take around a decade to complete on its own. That kind of delay, layered on top of the broader construction cost increases, has pushed the project's overall timeline significantly beyond its original target. The Tokyo to Nagoya section, once expected to open around 2027, is now realistically looking at operations sometime in the mid-2030s, nearly a decade later than originally planned. The project has also faced its own construction industry scandal along the way. Several of Japan's largest construction companies, including major names like Tyson, Kajima, Obayashi, and Shimizu, were formally charged with bid rigging related to contracts for the Chuo Shinkansen line, accused of colluding to divide up contract awards rather than competing genuinely for the work. It's a reminder that even a project framed around cutting-edge maglev levitation still runs through the same conventional, occasionally messy construction machinery as any other megaproject. So with costs climbing, timelines slipping, and years lost for environmental negotiation, why is JR Central still pushing forward with what's become one of the most expensive railway projects ever attempted? Part of the answer is capacity. The original Tokaido Shinkansen, despite being an engineering marvel in its day, is now operating at close to its practical capacity limit along one of the busiest, most economically important corridors on the planet. The Chuo Shinkansen isn't primarily framed as a replacement for that line, but as additional capacity, and critically as a form of redundancy. Japan sits along one of the most seismically active regions on Earth, and having a second, separate high-speed corridor between its 2 largest economic centers provides a critical backup in the event the original Tokaido line is ever disrupted by a major earthquake or other disaster. There's also unmistakably a prestige and technological dimension. Maglev has been a Japanese engineering ambition for over 60 years, and successfully deploying it at this scale, connecting 2 of the country's largest metropolitan economies, would cement Japan's position as the global leader in an entirely distinct category of high-speed rail technology, separate from and arguably more advanced than conventional wheeled high-speed rail that China, Europe, and others continue to refine. So where does this leave the project heading toward the back half of this decade? Tunneling continues across multiple sections simultaneously, with the newly unblocked central section of the Southern Alps tunnel now projected to take around a decade to complete on its own. JR Central has stated publicly that the delayed tunnel sections aren't expected to shift the overall opening target for the Tokyo to Nagoya segment beyond the mid-2030s, though the company has also acknowledged that further cost increases remain possible as construction continues through some of the most geologically challenging terrain in the country. What's clear is that the Chuo Shinkansen represents something genuinely different from most of the mega projects we cover on this channel. It's not a race to be first, since Japan has held the underlying Maglev speed record for years already. It's a race against geology itself, an attempt to bury an entire railway inside a mountain range specifically because the technology demands a straightness that the natural landscape simply refuses to provide at the surface. For now, boring machines continue grinding through fractured rock deep beneath the Japanese Alps. Engineers continue reinforcing tunnel sections that turned out far more fragile than anyone predicted. And somewhere, beneath nearly 1,400 meters of solid mountain, Japan is quietly building a railway that, when it finally opens, will let passengers cross from Tokyo to Nagoya without ever really seeing daylight.